Okay, how many have we got tonight? Henry and Marty tel nie, so ons is 'n hele 7 vanaand. Good evening to everyone I haven't greeted. We are continuing down the road to your exam for October, to make sure that you pass the RAE exam, which I have no doubt you will. And we're busy with building blocks. So every chapter that you're doing is one building block. And a lot of these building blocks, I think, will start making sense, yeah, from about the middle of August. They'll start making more sense because then we start looking physically at equipment. But one of the building blocks we have to discuss tonight is called, I just want to turn the 2 meters down, it's making a noise, is filters. And what do we do with filters? Now, the primary purpose of the filter is either to pass something or block something. That's what a filter does. It either passes something or it blocks something. Now, in terms of amateur radio, we get 4 types of filters, and we'll go through them in more detail. The first one is what we call a low-pass filter. So it means it...
Ekskuus Johan,
Yes.
gaan jy jou skerm met ons deel? As ek mooi vra.
My apologies. It's because we were looking at other stuff instead of the lecture before the time, huh? Okay, filters. My apologies about that one. Okay, hopefully everyone can see it. So, the primary purpose of the filter is to pass something or block something. That's what it does. And in terms of amateur radio, we're going to look at these 4 types of filters this evening. The first one is called a low-pass filter. So exactly what it tells you. Any frequencies below a certain selected or design frequency. In this case, on the graph, it says FC. So any frequency lower than FC is passed by the filter, and everything over FC is attenuated or blocked or stopped. High pass is obviously just the opposite. Anything below our selected design frequency is stopped, and everything over the design frequency is passed. But then we get 2 very interesting ones, which is actually more useful for amateur radio than the first 2. And the one is called a band pass filter. So I select 2 frequencies, and anything between those 2 frequencies are passed to the next stage of my radio or my transmitter. And everything lower or higher than those 2 design frequencies are obviously blocked or stopped. And then the other one, which we will discuss in a lot more detail when we do electromagnetic compatibility later before the exam, is called a notch filter. So anything, if I select a design frequency, I can set it so that anything lower than the design frequency is passed, and anything higher than the design frequency is passed, but at the design frequency, I'm blocking it, I'm notching it out. So those are the 4 types of filters which we're going to use in our radios and in our equipment moving forward when we get our licenses. Low pass filters. If you go back to your lecture on inductors and capacitors and reactance and resonance, all those wonderful things that you were taught a couple of lectures last week. Yes, last week. What's the characteristic of an inductor? Just take a moment and just think for yourself if you can remember what an inductor does. And if you remember the lecture, we said the lower the frequency, the lower the reactance or the impedance of the inductor is, and the higher the frequency goes, the higher the inductance, the higher the reactance or the impedance of the inductor goes. So you can already see at low frequencies, they will fly through the inductor. And at high frequencies, the inductor is going to say, hey, stop lorry, you're not coming past me. But then we add this little animal, which is called a capacitor. And if we think back of our lecture on reactance of capacitors, we said that the lower the frequency, the higher the reactance or the impedance of my capacitor is. And the higher the frequency, the lower the impedance or the reactance of my capacitor is. So if for any reason there is something that still manages to sneak past the inductor, the capacitor is going to short it out to ground, because this will have a low impedance, that will have a high impedance. So that's the principle of a low-pass filter. Something like in the old days around the fire, they used to talk about block and tackle, which is exactly what the circuit does. The inductor blocks and the capacitor shorts. So you can see low frequencies passes, high frequencies will get shorted out to ground if they manage to sneak past the inductor. So if they give you a picture or something in the exam of a filter, just think of your theory on inductors and capacitance, and what does the reactance of an inductor do with frequency? What does the reactance of a capacitor do with frequency? And you can work it out for yourself. High-pass filters now the opposite. So low frequencies is not going to be able to pass the capacitor, because we said at low frequencies a capacitor is a high impedance and an inductor is a low impedance. As the frequency goes up, the impedance of the inductor goes up and the reactance of the capacitor goes down. So you can work it out for yourself. So a low frequency will get to the capacitor and it will be blocked or stopped. If it does sneak past, the inductor is going to short it out to ground. And then as the frequency rises, this will pass the frequencies more readily or more easily because the reactance is going down. The reactance is going down and the inductor's reactance is going up. So this becomes invisible to my signal at high frequencies, and this becomes a short circuit for my signals at a high frequency. Okay, that's high pass. And that's the principle of all filters. If we look at band pass, now work out that same theory that we said, except here now we've got a series resonant circuit, and here we've got a parallel resonant circuit. And if we go back to our lecture on tuned circuits, what's the characteristic of a series resonant circuit? A series resonant circuit at resonance will be a low impedance. Okay? And a parallel resonant circuit at resonance will be a high impedance. So you can see if I'm at the frequency which I designed for, it will fly through the inductor and the capacitor, and this won't have any effect on my circuit because it will be a high impedance. So this becomes invisible at the resonant frequency, and this becomes well, I don't want to say a short circuit, but it becomes a very low impedance at resonance. If I'm before the resonant point or I'm after the resonant point, this is going to have a higher reactance, so it's going to block the signal. And these two together, if it is a low frequency, the coil is going to short it out, the inductor is going to short it out to ground. If I'm above my passband frequency, the capacitor is going to be a low reactance or low impedance, and that will short it out to ground. Okay, so before my passband, this guy does the work, and other side of the passband, the higher frequencies, this one does the work. And these two obviously are only on honeymoon and in harmony when they are at resonance. So at resonance, the impedance of the series tuned circuit is very low, so the frequency flies past. This one is resonating at that same frequency, so It's a very high impedance. It doesn't affect my circuit, and it goes past to the next stage of my radio. So you can work it out for yourself easily if they give this drawing for you in the exam paper. Okay, now we get to the next baby, the notch filter. Ever thought, how the hell do you make a notch filter? Fairly easy. Okay, this is a typical notch filter. So if we look at the frequencies above my notch, the frequencies below my notch. In other words, let's say as an argument, my notch is 10 megahertz. So the low frequency is 1 megahertz is going to come and it's going to run through these resistors, and it's going to my load to the next stage of my circuit. Okay, because it's a low frequency, these won't be in the circuit, so they won't be very effective. They will have a very very high reactance, the same as this one. So this C1, because it's got a high reactance, doesn't really feature at low frequencies. It's only the two resistors that feature when I do the low pass of my frequencies. At the notch, or other side of the notch frequency, these bottom ones are working. So remember, reactance of a capacitor goes down with frequency. So these two become low value reactances or low value impedances. So the signal passes right through them to the next stage. So that's a typical notch filter. It combines a short circuit for short circuit at resonance, and at the other frequencies it passes. Okay, next type of filter we're going to look at briefly tonight, because it's a very important part of a radio. When you get to modulation techniques with me around the middle of August, you'll see why we use a crystal filter. When I want to generate sideband signals, it's important for me to have crystal filters to separate my carrier and my other sideband out of my transmission. And a normal inductor capacitor filter is just not good enough. It doesn't reach home yet. So in any radio, you would find things which they call crystal filters. They are incredibly sharp band pass filters. It won't tolerate much below 9 megahertz, and it won't tolerate much over 9 megahertz either. And this one is a 1, 2, 3, 4 pole crystal filter, which is really, really sharp like a knife's edge to pass 9 megahertz from this side of my circuit to that side of my circuit. Did you do crystals yet? Trying to see now. No, you haven't done crystals. Yeah, we did crystals when we did capacitors as well. Remember, the crystal is a quartz crystal which has been cut to mechanically vibrate at a very specific frequency. So it's got an incredible high Q. Remember, we did Qs when we did tuned circuits. So this thing has got a Q very high, and it's made out of quartz crystal which has been cut to frequency and polished to that frequency. The other type of filter, which I wanted to show you the graph rather, you ever thought, those that have been exposed to radio yet, how is it possible for a repeater to receive on a frequency which is not very far away from its transmit frequency? There's a very special type of filter we use on repeaters, which is called a cavity filter. So if we look at this graph here as an example, the blue would typically be my transmit frequencies. So you can see at my receive frequency, I'm notching out my transmit frequency. And then at my transmit frequency, I'm passing my transmit frequency fairly well. On the receive side, the red curve, I notch out on the receiver my transmit frequency with this very sharp notch, and I pass my receive frequency through to my receiver. And cavity filters is what makes it possible for us to have radio repeaters sitting on the mountain to use. We use cavity filters. Okay, when we look at filters, you will see they talk about half power frequency. Remember our dB lecture? Half power of twice the power is 6 dBs. Sorry, I'm lying. Twice the voltage is 6 dBs, and power is 3 dBs. Now, what they typically do is they talk about the half power frequency. Just want to see. Somebody's talk about the half power frequency, which is minus 3 dBs, and you look at the slope of your filter. And the slope is defined per octave. And what is an octave? 100 hertz to 1 kilohertz is an octave. 1 kilohertz to 10 kilohertz is an octave. 10 kilohertz to 100 kilohertz is an octave. And so you can carry on. So if you look at this filter, this is a fairly lousy filter, number one, because it's 3 dB point is, I see they've put all of them as the 3D minus 3 dB point 1 kilohertz. But if you look at it over an octave, it's only got 20 dBs of attenuation. This low-pass filter is a lot better. It's sitting on 40 dBs per octave. And this is normally dependent on how many inductors and how many capacitors I use to make up my filter and the configuration of the filter. And so we can carry on. This last one, number 5, for example, could easily have been a cavity filter because it's sitting at minus 100 dBs per octave, which is quite good. It's not bad. So in filters, we talk about the slope. The same goes for a bandpass filter. A bandpass filter, we look at the half power frequency, minus 3 dBs, and we say the bandpass filter would pass from this frequency all the way to this frequency. So that's the bandwidth of my bandpass filter. So I purely measure this graph and I calculate the difference between the two. Okay. Where do we use these filters? Just to summarize, filters enable radio receivers to only see the desired signal, and it gets rid of everything else. Or it passes the desired signal. Okay. Power supplies, I think you're doing power supplies with Henry next week or this week. You'll see why we have to use filters, because we need to eliminate either high frequency noise that's on the power lines or low frequency noise that's on the power lines. So filters, essentially, because I say it's used to block or pass something, that's why we use filters in radio equipment. And that was a short and sweet lecture. It's not long in your books. That's why it was so short this evening. Any questions from the floor? Dead silence. Okay. Come on, stop sharing. Okay, let's go to our books and let's have a look at what we have here. Questions in the book. A bandpass filter allows all frequencies, attenuates all frequencies, allows signals between two frequencies, increases bandwidth of a receiver.
C.
Signal, yeah,
C, allows signals between two frequencies. Yes, a bandstop filter allows all frequencies to pass, attenuates all, decreases bandwidth, attenuates signals.
D. D.
Yeah, between two attenuates.
It attenuates signals between two frequencies. They call it a band stop here, but it's the same as a notch filter. The engineering term is actually a notch filter, but yeah, so you know. Low pass filters. Attenuates all signals, introduces harmonics, removes RF signals, requires the use of high gain amplifiers.
A.
A. Attenuates all signals above a known cutoff frequency. High pass filter.
The opposite, D.
D.
Yeah.
D.
D.
Okay. See, these are Mahala questions. If you get these questions in the paper, it's like Mahala. You can't get them wrong. A circuit which passes electrical signals above a certain frequency but blocks electrical signals below that frequency.
High pass.
Sorry?
C.
High pass.
C.
Yeah,
A
C.
circuit which passes signals above a certain frequency but blocks signals below that frequency is a high pass filter. Yes. Okay, then the purpose, just scroll this up. Purpose of a low pass filter is to
C.
C.
C, yes, or pass all signals below a specified frequency. See why I say these are Mahala questions, you can't get them wrong. The purpose of a high pass filter is to
D.
D, attenuate
Yes.
all signals below a specified frequency, but pass frequencies above it. Yeah. And then the last question, 8, a low pass filter seems to be letting through harmonic components that it is supposed to suppress. The design has been checked and all component values are correct. The reason might well be that.
D. Any of the
Yeah.
above.
Any of the above, yeah.
Correct. Any of the above. Especially when you start working with higher frequencies in the hundreds and gigahertz of gigahertz region, things that are too close to each other is giving you a lot of problems. So it becomes incredibly difficult to design things the higher the frequency goes. Okay, that was it. Henry?
Right, ek gaan die opname stop. I'm going to stop the recording.